Okay, so there will be a slight, well, I shouldn't say slight, there will be some meaningful extension to the top-down parsing. There's something called backtrack-free parsing. From its literal meaning, we want to get rid of backtrack. But for your assignment number 3, I would suggest you try the backtracking version. But if you really insist, you want to implement this particular backtrack-free version by calculating the so-called first and also follow set. Well, that's something we will cover only next week. But if you really want to do it for yourself, that's fine too. Okay? I'll be quite flexible with that. But let's talk about why. We just need some extension. So the TD parse that we spoke about last Thursday, that one will optimate the top-down leftmost derivation. And I said leftmost because left recursive grammar will cause infinite loop. All right? And then very inefficient, especially got backtrack. Right? A very, very quick visual here, basically. Think about what's happening here. This is the, This is the grammar we spoke about in detail last Thursday. Okay? Let's say this is a tree we start with. Of course, we start with the goal. Oh, by the way, it's just another grammar. Okay? Let's say we start with the start symbol here, start variable. Let's say we are now here, term prime. We knew from last time, when we get to term prime, we got 1, 2, and 3. 3 possibilities. Each one of them is going to involve, for example, let's say if we happen to pick this one here, and etc. And then we're going to build these nodes over here. And later on, we might just find that this particular symbol here, for example, is not really matching the current word, in which case we have to get rid of these and then backtrack to here. And we're going to try the next rule. And if that doesn't work, we're going to try the next rule. That's basically what the nature of backtracking is doing. Would it be possible to make it more efficient? Indeed. The idea would be, when we are at this point over here, before we know which rule to apply, we may just want to so-called look ahead for one symbol. In this case, of course, it's very obvious. We look ahead to see this is a multiply, this is a divide, this is epsilon, to see which one it might be matching the current word. If it is matching, we choose that one. We don't have to worry about wasting our resources doing backtracking. Right? That's kind of the general idea for why we can improve the TD parse algorithm. Okay? And basically, this slide here just tells you that there is such a notion called the look-ahead symbol. This is something we would like to use in order to save us some time for doing backtracking. In order for you not to do backtracking, you ought to know if I choose this particular rule for derivation, am I really going to hit that symbol to match the current word? If I can, of course, I'll go for that. If I cannot, I'll just simply wouldn't build a subtree, right? I want to really avoid backtracking. That's basically what we said last time, just remember. And we talked about the first set. If you recall this little page over here that we did last time, right? So this idea would be, if I want, let's say now currently I got expression here. If I want to choose this particular rule, for example, in that way, what will be the very first symbol, terminal, I will actually see? And we actually got some intuitive calculation last time. It's pretty much what the algorithm would do. So that's why we don't need to spend too much time today. But I'll show you the algorithm and also show to you the pattern matching part you have to watch out for. Okay? And everything else will be up to you. Okay? Let's now, first of all, go over some definition for the first set. Okay? Oh, so here, I don't need to go over. That's basically from your project description about milestone 2. Nothing has changed, but I'll make it more concrete when I release the PDF, most likely tomorrow or by Thursday's class. Okay, so that will be the algorithm for the first set. Let's try to look at these two together. Okay? Let's focus on this one first. This is more like an abstract definition for the first set. Okay? The alpha here, okay, let's take a look. Whenever you want to do a computation for the first, you can pass on alpha. Alpha can either be a terminal, like a symbol, or it could be a variable. there are two cases. In the case where the alpha is simply a terminal, what will be the first set for terminal? What do you see first in a terminal? Well, just the terminal itself. So that's why it's simply just alpha. That's very straightforward. You can think about that's the base case. What about the recursive case? If you actually got some variable over here, basically what you need is to somehow go through some derivation step. Right? You can see that exactly over here. In order for me to figure out the first of certain variable, it's going to be all the words. So you can think about the W here, all the terminals or the words. That's why you see W is simply sigma star, right? There's no variable here. All such W, alpha is able to be derived into something starting with W. And the beta over here is something we don't care. Okay? You can think about W is the starting symbols. And such string can be derived from this alpha, which we want to calculate its first set. Okay? That's the definition. And yep, that's the abstract definition. That's something you can maybe spend a little bit more time looking into once we have gone through the algorithm. Any part of the definition you are not so sure about, you want me to go over. But I think that's pretty much it. Okay? Just remember, the W over here should be all terminals. That's something you will see. Okay? But how do we calculate this using an algorithm? How do we do that? Okay, let's take a look. So this is the algorithm over here. Okay? It's simply just called get first. The input will be a context-free grammar with variables, terminals, rules, and also stop variable. And you can see T here is simply just a terminal. That's fine. What will be the output? And this is something I want to emphasize. The first over here, you can think about the first. Remember this symbol over here that actually we spoke about, maybe back in the DFA or NFA formulation. It is a function, right? Just remember. Or think of it more like a hash table, like a hash map. What will be the key? The key for the map will just be either a variable or a terminal, or simply epsilon or EOF. So these are the possibility as the key. Whenever you pass anything as the key that's valid, it's going to return back to you a set of terminals as the first words. That's a computation. Okay? So the way to read this would be, so the first. So you can think about given a valid terminal or non-terminal, return its first symbols, leading symbols if you want to think of it. Okay? And let's now go over this algorithm quickly. It's actually not that complicated. You just need to understand mainly just about the for loops over here, which I'll definitely give you some intuition. It's mainly here, but we'll get there. Before that, let's take a look at the initial stage. For this part over here, this is just building up the base cases. The first for terminal. If you remember back in the definition, for any alpha that is a terminal, the first will just be a singleton set, just the terminal itself, right? That's what we're doing. For all the alpha that is a member of the terminal, EOF or epsilon, the first of alpha will just be the alpha itself as a singleton set. That was easy. And then initially for all the variables, we just let its first to be just empty. We don't have anything just yet. Okay? And then this part over here is a little bit similar to one of the algorithms that we did previously. I'll tell you what it is. Remember how we compute the lazy evaluation for the DFA, right? Converting from NFA into DFA. We said that the while loop itself is looking for some fixed point. As soon as you get to a point that you cannot really make any further new discovery, in that case, you stop the loop. Similar over here. So what you can think about is, as soon as we reach a point that the first map cannot be grown or updated any further, that means it's now time to stop. So we don't really go indefinitely. Okay? That's really important to also observe. You can think about, as soon as the first map cannot be grown, and then you exit from the loop. Okay, that's kind of the inside. But let's take a look what you're supposed to do. When you actually calculate it, let's go over quickly and we'll do one example. The main pattern to see is like here. We say for each production rule that has this kind of form, you can think about the first component is called beta 1, and second component beta 2, all the way to beta k. Okay? That's how we start with. And then we're actually going to collect some information from beta 1 for sure, but we only get to beta 2 if somehow beta 1 is nullable. Do you remember the notion about nullable before, right? Okay, intuitively, let me show to you. Intuitively, if I know, okay, let's take a look here. That's exactly here. Let's say this is the layout for A. Beta 1 over here, we want to think about what is beta 1. If the epsilon is a member of the first of beta 1. Okay, this is case number 1. And we also got case number 2. It is not a member. Okay, let me write it down and I'll explain. Epsilon, not a member of first of beta 1. We got 2 cases over here. And let's pause a little bit to think about case number 1 and case number 2. What would be one example of case number 1? I'll show you the grammar here. If you look at term prime produces epsilon, that means it is possible when you actually want to use this rule, the first one you see is actually an epsilon. That makes no contribution to the ultimate string, just epsilon. That'll be case number 1. Case number 2 would be when epsilon is not in the first. What will be one example? One example would be, let's say this one here, factor. You can see in order for me to choose the factor, I can see the first character either being the opening parenthesis or some number or some name. There's no epsilon over here. So this is kind of the case where we can see the symbol right away. There'll be no need to go any further to beta 2, beta 3, and the beta k. Okay? Right, let me write some annotation here and then we can move on to the algorithm. So for case number 1, when epsilon is there, so that means need to move on to beta 2, right? We want to look at beta 2, and the same pattern will go on. Beta 2, there are also 2 cases. Either beta 2 has epsilon in its first set, or beta 2 does not have it, right? Follow the same pattern. You will see that exactly in the algorithm, which I'll show to you. And for case number 2, when epsilon is not there, that means stop right here. No need to go to beta 2. So after I have gone through the example with you in the next page, you can definitely review about these 2 cases. For every component over here, you just want to see if beta 1 is nullable. In that case, I might have to collect beta 2 as well. If beta 2 is also nullable, I may need to look at beta 3. Another scenario, if beta 1 is nullable, of course, I look at beta 2. But let's say beta 2 itself is not nullable. In that case, we don't really need to look at beta 3. We just stop there. That's why you will see there is a loop over here. I'll help you a little bit to gain some intuition from this loop. Can somebody tell me, based on the for loop declaration here, under what circumstances do we actually exit from the loop? Precisely. A Boolean condition. What Boolean condition should we? Of course, you will need to look at this middle part here, right? But this condition here tells you under what circumstances you have to stay in the loop. To exit from the loop, it needs to be its negation, right? Exit when either the epsilon is not in the first of the current one we're looking at, or we are reaching the end, I larger than or equal to k. Right? This Boolean condition here actually is very important, especially the first one. The first one over here, when we say epsilon is not in the first of the current component beta I, that means we should stop here. Don't really try to collect the first components from any later components. And that's exactly case number 2 that we talk about over here. So when you study the algorithm, try to link this exit condition here to case number 2. All right? And here we say as long as we actually got more beta I that's nullable, we can keep collecting it until we hit the wall with something that is not nullable. Let me put it here. Keep collecting. The first until is not nullable. All right, and finally, the final condition here is what I highlighted here, and then look at this one here. This one is to say if the loop counter here is exactly equal to k, and remember we only got k components, that means we have now reached the end of the components for this variable a, and everything is nullable. What does that mean? That means a itself is also nullable. If a is nullable, then epsilon must be in its first set. Okay? So here that means every component, okay, every component of A is nullable. That means A is nullable. In that case, we should really include the epsilon into its first set. Right, it's a very quick walkthrough about what the algorithm is supposed to do. And then we're going to do an example. All right? All right, spend some time with the algorithm after class with yourself, and then come back to me if you got any trouble. Okay? Let's now look at one example. Okay, so how are you supposed to trace? We wouldn't trace completely, but I'll just give you some idea. Okay? So here is some principle. You should really choose, let's say we are given this grammar here, so that's the input. And the output should be, you can think about the first is more like a map. So you can, these are the keys of the map. It can be some terminal over here, and these are the variables. And the value should be the corresponding first symbols for the terminal or non-terminal. That will be the output. And the principle will be, you want to choose the rules in certain order. I would say the order is really arbitrary. It's kind of up to you. Okay? But for me, I'm going to cheat a little bit. I want to choose this particular order, just easier for us to see. In case you got this question on the quiz or the exam, you can choose any order you like to really do the first set calculation. Because as long as you don't really reach the fixed point, you should really keep going until you cannot really go any further. All right? So that's a grammar, which we looked at last time very briefly. Okay? Let's now take a look. Let's do the simple part. This part over here, simply just build a base case. For every one of the terminal and also EOF and epsilon, the first set will just be itself. So for none, it will just contain none. For name, it will just be name. Plus, minus, multiply, divide, opening, closing, EOF, epsilon. Base case, very easy to build. And then, initially, we're also going to initialize all the first set for the variable 1, 2, 3, 4, 5, all to be just empty to begin with. That's all we're going to do. Okay? And let's now dive into this loop to see what's going to happen. Okay, this loop. Okay? And let's say, let me choose F to be the first. Okay? Factor. If I look at the factor over here, that'll be the first iteration, factor. And then I got the first rule I'm going to check would be factor produces, let's say, you can think about this is more like a beta 1, like a beta 2, and beta 3. Okay, think of that. Okay, this will be a very representative example of what a loop is going to do. And it's a simple case to handle. Given that we got beta 1, beta 2, beta 3. And then, do you guys know if we should do anything over here? It turns out, in this case, let me start with this. Here, what will be the first of beta 1 over here? You can see the beta 1. Let me put it here for the very first iteration. So we got factor produces this, also expression, and also this, right? Let me be more precise. So that's beta 1, beta 2, beta 3. Okay? What would be the first of beta 1? Should be over here. That's how we start with. Okay? And then set difference, the epsilon, you will have no effects because epsilon is not there. And then we're going to run this loop. And for this loop over here, how many iterations are we going to run? Remember the purpose of this loop. It will try to maybe collect, for example, let's say here, beta 1, beta 2, beta 3. If beta 1 happen to be nullable, in which case we have to also collect the first of beta 2. Is this the case? No, it is not, because beta 1 over here is actually not nullable. So we just stop there. So we don't even execute here. It's not executed. Okay? I'll write a note here. So this one here, this part over here is not executed because the first of beta 1 over here does not contain epsilon. It does not. Okay? So that means eventually what's going to happen is we'll simply keep just the first of A. In that case, which just accumulates this symbol over here. It will just be this symbol here. So after the first iteration, we'll simply get, for the factor, we just get this. That's after the first iteration. We just collect that. What about the second rule? Well, the second rule would be we just go for this one here and also this one. Both of these are also not nullable. We just keep growing. All right? So that means after the next iteration, we get this and also the num. And after the next one, we'll get this and the num and also the name. Okay, so this will be the calculation for the first of the factor. So this will match what we actually got intuitively last time. If you look at what we got last time over here. So I would say depends on how the question is being asked. If I just give you the grammar and you just want to figure out the first set, you might just be able to just look at this and see, okay, that's a terminal, collected. That's a terminal, collected. That's a terminal, also collected. That's the intuitive way. But you ought to also understand how the algorithm will also make it work, just over here. Okay? Are we okay with this, just for now? Why don't we do one more? And then I got a little challenge for you that you can think about. How do we compute? Let's see, okay, I gotta watch out the time. How do we compute over here, let's say the E prime. Let me use a different color here, E prime, expression prime. How do we compute the first over here? And there are 3 rules to go over. Rule number 1, rule number 2, and rule number 3. All these, right? What's going to happen is you can see the plus and also minus. So these are terminals, in which case we just collect them without going any further to. You don't really go here. You don't go here. So for the expression prime, first of all, you will get a plus, and then you will get plus and then minus. And the final one is going to be the epsilon. Okay? The epsilon, if you try to trace this code over here, what you just remember, whenever you got epsilon, it would just be collected right away. Because it's only this one here. You don't have any further components to actually collect. You just collect it. Okay? Plus, minus, and epsilon. This input grammar here is rather straightforward. You don't have any special case where you will go beyond beta 1. But I'm going to give you one case where you might have to go beyond beta 1. Okay, I'll give you one case. Okay? Right? If you want to continue, you can continue with the term prime, term, and also expression. The algorithm itself is very straightforward, so you don't need to worry too much. So here's one little exercise for you to think about. Okay? Hypothetically, let's say we want to add this rule to the grammar. So that means for the expression prime, we want to add another alternative. Okay, so you can think about here, or term prime factor. Okay, that's the change I would like to introduce. Don't worry too much about whether that really makes sense for the ultimate language. But I want you to really look into this to see the following. If I got term prime, for example, we know that term prime is nullable, first of all. And then, later on, when we try to execute this line specifically, is it going to run for one iteration or no iteration? It turns out it will actually run for one iteration because given that this is, remember we actually got a pattern, beta 1, beta 2. So you can think about this is beta 1, this is beta 2. In this case, we know epsilon is actually a member of the first of term prime. Right? You can see epsilon is over here. So that means when we actually want to collect the first of expression prime, it's going to be, of course, plus, of course, minus, of course, epsilon, and of course, it's going to be the first of term prime. It's going to be the plus, the minus, the epsilon, and also the first of term prime. And the question is there anything further? Indeed, because since term prime over here is nullable, so we should also move forward to look at a factor. So we also need to collect all these as well. Okay, that's the critical point I want to show to you. Also union with the first of factor. All right, that's the main thing to show to you. Okay, so we talked about this algorithm last time about calculating the first set. So this is the abstract definition, and that's the algorithmic specification. We also did the detailed tracing together. Okay, that's the only thing we did last time. And today, before we actually talk about the need for another set called a follow set, we want to just do a little bit of extension about the first set, which is kind of implicit already in the algorithm. Right? So if you recall from the algorithm, you can also check the input over there is simply a single variable or a single terminal. What do I mean? So if you recall what we did last time, I'll show to you very quickly. When we actually calculate the first, for example, we say the first of some expression prime, which is a single variable. What we want to see today in the beginning, what if I want to calculate the first of this entire rule, which consists of a mix of symbols and also variables? That's something we want to see. That'll be very useful, actually, when we later on want to put everything together to get the backtrack-free algorithm. Okay, we'll get there. So the first thing to clarify is the first set calculation originally that we talked about on Tuesday is only a single variable or single terminal. What we want to do now is to have something like a star, meaning that we can have the right-hand side of the rule. And the calculation is actually very straightforward, but I'm just going to use this opportunity to recap very quickly how we can do the calculation. And sorry about this part over here. I will make sure I fix the slides, but on the iPad page, it's actually fine. So let me just switch there, and then we'll just look at some example quickly. The name of the extended function is still called first. But whenever you got the first over here, if you see only a single variable or single terminal, you would know it's the original version. But if you see a list of variables or list of mix of variables and terminals, that'll be the extended version. Let's take a look. Okay. Let me, first of all, actually go over this definition with you very quickly about the first. Okay? And let's remind ourselves what first is really about. Whenever you're given beta 1 can be a variable or a terminal. Right? The beta over here can be a variable, or it can be a terminal, either way. And when you say you want to calculate the first set of this or this, what do you really mean? You're saying that if I try to derive this particular variable further, what will be the first symbol I'm going to observe? What will be the possibility? By using the list of possible derivations, we will be able to avoid backtracking. So that's kind of the intuition we had before. And in the terminal, it's simply no-brainer. Whenever you see a terminal, that'll be the first symbol you see. There's no further derivation needed, right? So these are the two possibilities that we talked about last time. And now let's say, rather than having a single variable or a single terminal, what if we have a list of mix? Beta 1, beta 2, all the way to beta n, all right? And you will see we're just doing a list of union over here. Okay, you definitely need to spend a little bit more time after class to think about this formulation. And that's a set comprehension, apparently. I'll give you some insight here right away, and then we'll do some example. Okay. Number one, you want to see we got from 1 to n. We got n components as the argument. And then here, when we talk about union over here, we only go from 1 until k. And there's a reason for that, right? Under the condition that we're saying that every beta from 1 until less than k, that means k minus 1. What we're talking about is from beta 1, beta 2, and also all the way to beta k minus 1, right? That's something you can read right away. What would be the common property of the first k minus 1 components? We're saying that they are nullable. What will be the consequence when these components are nullable? For example, let's say, if I have, let me just write it down again so you can see it more easily. If I got A, for example, produces beta 1, beta 2, all the way to beta k minus 1, beta k, all the way to beta n, right? That's the original input. Let's say up to this point over here, every one of the components are just nullable. And if you recall what we did, in order to remove the null production, when we say nullable variable, that means you have to think about either this component here is there or it is not there. When it is not there, you definitely have to consider the first of beta 2 as well. And where beta 2 may not be there, you also want to consider beta 3, and etc. So there are 2 to the power of k minus 1 possibilities over there. Okay, so that's kind of the intuition. So what we are saying is, if we know that from 1 until k minus 1, each one of them is actually nullable, then we can definitely union all their first set together because they are all possible to be observed as the first symbols. because their previous one may just be nullable. And this will be some very useful insight when we calculate the follow set a little bit later. Okay? And of course, if you see on the slides, you will see beta k is the first one where it's not nullable anymore. That means you cannot really go any further. Okay? Think about this intuition when you study the slides. Right? This will be the first components that's not nullable. So we don't have to collect the first set any further. Nullable. So that means no need. And we're going to do examples right away. There's no need to collect the first further. Okay? So this will be the first one. So that means we stop there. Okay? Let's now take a look at some example. And you will see on the slides over here, the first one we want to calculate is this. What will be the first of this? Number one, you want to observe that we are trying to calculate the first of not just a single variable. We actually got two components here, term followed by expression prime. Right? So what should we do here? This is a very simple case, but let me give you a little bit of intuition here. In order to calculate the first of this particular list of components, we want to know what's the first of term for sure. That's going to be observed. When should we consider also the first of expression prime? When term itself is nullable. Okay? So let me write it down here. So the first one. So when you want to calculate, for example, the first of term followed by expression prime. Okay? You definitely have to consider for sure the first of term. In order to see what you can observe from this particular list, definitely the first one to observe will be the term itself. That one's for sure. But should we also consider the first of expression prime? We only consider this if the term itself is nullable, meaning that there's a possibility that this part here is derived into epsilon, in which case we have to figure out the first for expression prime as well. But is this the case over here? And what we assume is you already know about these two tables which we calculated last time. So if you look at the first of term, if you look at that here, the first of term, do we have any possibility of epsilon over here? We don't. We either got closing, opening parenthesis, or we got some identifier, or we got some number literal. So none of them will make the term nullable. All right? So that means in this case, I'm going to make a note over here. Expression prime over here, not nullable. Or to be more precise, epsilon is not a member of the first of expression prime. So in this case, that's all we have to calculate. Okay? What would that be? That would be just the first of term, which would be all these. This, the name, and also the number. That's what you will see over here. Like that. All right, are we okay with that? William, go ahead. Question. Huh?
I feel like at some point you said that expression prime is not nullable.
Turn. What I really meant to say the turn. Yes, I meant to say turn. Yes. Okay. Maybe I did it. Okay. In that case, I really meant to say, okay, let me say that again, just in case. Maybe you're right. In order to calculate the first of this particular list, you definitely have to include the first of the term over here for sure. And you want to make sure, oh, I see. I see what you mean. You only get to this if the term itself is actually nullable. Okay, I see what you mean. Let me just write it down here. You're absolutely right. Let me just correct this. That's absolutely right. Okay, that will make more sense, wouldn't it? So here, the term, as you can see, is exactly over here. It is, term, not term prime. The term over here. Okay, you can see the term here is not nullable. Because epsilon is not in the first of term. That means you don't have to consider expression prime first. You don't have to. Only consider that. Good. So the easiest way to remember how to calculate this is to see, start from the leftmost. If the leftmost is not nullable, you stop there. If it is nullable, you have to keep going until you reach a point that you hit a wall, meaning that it's not nullable anymore. Just remember that. All right? Let's now take a look at another example over here. What about this? Guys, how do we calculate the first of this list over here? Let's follow the same principle, right? There are 1, 2, 3 components over here. We always should include the first of the first components. The first of plus will just be a plus. That one's easy. Should we also collect the first of term? Should we or should we not? Shafan, should we? Should we collect the first of term in this case? Okay, maybe William.
Well, plus is already terminal, so I think
We're done there, exactly. It's that easy. Okay? All right. Again, just repeat. In order to calculate this, you want to always include the first of the first components. If it's already a terminal, you definitely don't have to continue further. If it is nullable, you have to continue. Okay? Like that. And this one will be done similarly. Because minus is a terminal, you don't have to collect the term over here. Right? You already hit the wall, so you don't really reach any further like that. Okay? And this epsilon here would just be epsilon. Okay? But I believe do I have any other example over here? You know, there's something we can take a look. Give me a moment. Term prime. That's okay. We can look at the exercise sheet maybe for later. But, okay. Are we okay about the computation for the extended first? This will be something we assume we're going to be doing. Okay? So this will be the first calculation, and we have to now realize this itself may not be enough for the backtrack-free grammar. We need something more. But let's see why, and then we'll get to that second set. Okay? Okay, let's see this. Okay, is the first set really sufficient? And this is actually something we did earlier in the lecture for the tracing about the top-down processing. But we're going to look at that a little bit later. But let me go over a little bit more bullet points just to see why first set is not enough to ensure backtrack free. Let's say this. Let's say we have these, this particular expression prime. Let's say expression prime has 3 alternatives. Either we can do plus, we can do minus, or we can do epsilon. All right? And we know pretty well from before the first of this particular alternative. Okay, let me just do this. Some very quick exercise you can just do on your own, but there's something we already did as a preparation, right? You can say, in order to figure out what the consequence of using this rule, we know the first of that is simply just plus. We know that the first of the second alternative over here is just minus. Okay? And the first of that, the third alternative, is actually epsilon. Okay? And this is really a special case that we may want to handle. Of course, by the way, one may argue that before you actually treat the grammar, you can always remove the epsilon production, like what we did earlier. But sometimes you may still be given some grammar with the epsilon production. That's also another possibility, right? That's why we are talking about this. This is problematic. Okay? Why? If this is only epsilon, we cannot really make a decision right away whether or not the focus is matching the word. Because the epsilon over here, if you kind of recall what we did earlier for the tracing, I'll just hand wave a little bit so you can definitely refer to what we did earlier. Let's say this is the epsilon. Okay? and the current word is actually plus. So we don't really know whether choosing this epsilon is really going to hit somewhere that's going to have derive into plus. We don't really know. We wouldn't know until we actually get to maybe several backtrack steps until over here, and then go from there and see if plus can be derived or not. If it is, we're lucky, then we hit. If it is not, then we have wasted resources doing backtracking. So wouldn't it be nice if we can avoid that kind of backtracking? So the idea would be, we want to say, considering first would be useful, for sure, in these cases. But wouldn't it be nice to say, what about after expression prime is derived? What can come after that? So this is a new concept that we want to learn. Before we talk about the first is about what are you going to see right in the beginning. And we're going to consider another one would be what would you see at the end after the derivation. So that one there is going to help us to actually save some backtracking in this kind of case. Right? That's what we'll see. All right? So from this one here, we say it would be nice, useful. Useful if we can know what symbols follows. So this will be the keywords. Follows expression prime. Okay? So this is the new bits that we're going to learn before we can actually have a backtrack-free grammar. Right? So we have done the first, and we have seen the motivation for the first not being sufficient. So now we're going to talk about another new set called the follow set, and we're going to calculate it. The way it's going to be calculated is not too bad. I would say in some way it's going to be calculated in a very symmetric way as the first set. So I'm going to show you the algorithm. We'll do some example together, and then we'll see how to put them all together into the grammar. Okay? Okay, and for the rest of the slides, it's basically just about the motivation, why we want to do this. Are we okay so far? Up to here. All right? What we want to do now is to see this new set over here. Right? So ultimately, you're going to see 3 sets in total. So you want to really know what they are really meant for. The first is really by observing what can come first before the derivation. Follow will be what can come after the derivation intuitively. And there will be another set which we're going to define in terms of the follow and the first. We'll see. All right, let's take a look at the intuitive definition. It will be the set of symbols that can appear to the immediate right, like after the string derived from V. Right? Of course, the argument for the follow will just be a single variable. Okay? Or we can generalize it into a mix of symbols, like what we did to the first. This will be the abstract definition. Let's now take a quick look. Okay? For now, we're just going to talk about variable. Okay? Let me use a different color here. Whenever we want to calculate a follow set for a particular variable, what would that be? Okay? It's going to be all such words, W. So what will be the condition for W? You can see W here is simply sigma star. So it's terminals only. First of all, it's terminals only. It does not contain any variables. Terminals. Over here. Okay, and let's take a look. V over here is the argument we pass. If the V can somehow be derived into some string X. Okay? And then this will be the start variable over here. And this will be the start variable. And then take a look at this particular string. Okay? You can see here, X over here is derived from V. And W is just another string that follows the derivation of V. A string that follows the derivation of V. And what about the Y here? Y here is just for pattern matching, just the rest of whatever the derivation is. Okay, let's recap what the definition is telling us. Whenever you're given a variable V, you want to calculate all its follow symbols. It's going to be all such words such that after certain derivation x of V, there will be a words that follows that. That will be what we want to calculate as a follow symbol. Okay? And you can think about the way we calculate this follow set here is going to be very symmetric to how we calculate it first. Rather than calculating from left to right, we're going to calculate from right to left. That's going to be how we're going to do it. All right? And let's have some intuition over here. Okay? I already got answers about the follow over here. Okay? We can go over a few of them just to get some intuition, and then we'll see how the algorithm should work. But before that, we're going to do a little bit preparation exercises just to make sure you're okay. Okay? And whenever you want to calculate a follow, there will be some very important assumption. We're assuming that you have already calculated the first set. It's available for you to use. Okay, I'll write it down. Important assumption. Important assumption. The first is already computed. Okay, that's really important to note. And I just put it here. This will be the first over here. All right. So as we go over them one by one, I'll see how many we should go through. At least we'll go over the first few, and then we'll see. Let's start with the expression. What will be the follow for expression? Okay. The way to think about it is you want to find every occurrence of expression to the right-hand side of each production rule, number one. Okay, let's find it out. You can see over here, expression appears over here. Okay, let me make it thicker. The expression here, and we got another expression over here. Right, we got two occurrences. Only look at the right-hand side occurrence. You don't need to look at the left-hand side. Okay? Of course, it's a little bit different. Before, when you calculate the first set, you have to look at the left-hand side to look for the variable, to calculate it first. But now for the follow, you have to look for their occurrences on the right-hand side. That's something to note. Okay? And let's start with this one. This one is rather easy. Okay? We are saying somehow expression can be derived to something. What can follow that? Well, this guy here. That was obvious, right? Okay, so that's why you see this guy over here. Okay, that's why. Number one. Number two, given that goal is the start variable, we assume that at the end of the entire derivation, there will be an EOF, end of file symbol. That's always assumed. Okay. So you can think about at the end, there's always an EOF, always. So that's why you will see EOF over here, and also the closing parenthesis because of this. That's how you can interpret the follow for expression. We can look at a few more. Okay, let's look at a few more. What about the second one? Let's look at expression prime. Expression prime here, here, and also here. I believe these are all the three occurrences, right? We got only three. We're going to consider them quickly. Let's first of all consider this one. This is like a special case in the sense that expression prime happens to be the rightmost components of this particular production rule. So what follows expression prime would be just the same as what follows expression. Do you see what I mean? Let me show you. If I got expression over here that can produce turn, follow, expression prime. So think about what can follow this. They can also follow that. Okay, that'll be something to remember. Okay, that will be something you will see from the algorithm too. Okay, I'll put a mark over here. So this is why you will see. Let me use the green. You will see for expression prime, we simply inherit EOF and closing parentheses. So these are simply just the follow. of expression, because expression prime happen to be the rightmost component of expression. And what about these two? Similar, expression prime should be the same as what follows expression prime. Well, it has no effects. All right? And that's about expression prime follow. Right? I think this kind of intuitive walkthrough kind of gives you some idea what the algorithm will actually do. I'll show you different parts in the algorithm. Okay? And then we'll do a little bit more mechanical calculation. Okay? Let's do maybe another one. How about turn? Again, let's identify all the occurrences for turn. So we got here, and anything else. We got here too. Okay? Guys, this one's interesting. Okay? Especially, I want you to actually look at this one here. Oh, you know what? Let me use the same color. Okay, let's look at this one here. Now we want to calculate the follow of the turn. That's what we want to do. Okay? Turn is not the rightmost components. So in order to observe what can follow the turn, we don't necessarily can just calculate the expression prime its follow. It might work, but in general it may not work. So let's see in this case specifically. If you look at expression prime, okay? Expression prime over here, if you look at its first, which we assume exists, it includes epsilon. What does that mean? That means there is a chance turn may be the rightmost components of expression if this happens to be null, given that its first includes epsilon. I hope you're following the logic here. All right? In that case, turn, the follow of turn is going to inherit everything also from the follow of expression, for sure. I'll write this down a bit. So here for the turn, so that will be EOF, and also this one here. So these two, okay? So these two are simply the follow of expression. So that is, we want to calculate the follow of turn. It turns out the follow of expression should be included there because this rightmost components may be nullable. So that's why it can also follow. Okay? So that one there is simply follow because the first of expression prime, which is over here, the rightmost, contains epsilon. All right? That's something you can also look at. Okay? And these two will follow very similar logic over here. And we're going to maybe look at them maybe when we calculate using the algorithm. That's something we'll do. But I think intuitively, you have seen quite many interesting rules already. Let me recap very quickly. Okay? Only look for, if you want to calculate the follow of certain variable, only look for the occurrences on the right-hand side of the production rule, number one. Number two, if the variable happens to be the rightmost, in that way, inherits the follow of the left-hand side over here. Number three, if somehow the variable happens to be in the middle, not the rightmost, in that way, you have to look at the previous one. If they all happen to be nullable, in that way, you have to include this one as well. Okay? So we can definitely generalize this a little bit further. That's something we will do. Okay, follow set. Okay, before the break, we talked about just intuition. Now we make it more precise. Okay, and I will highlight certain lines you should really look into a little bit more when you can stay by yourself and then to convince yourself. But what I want to focus more is to show to you in the test how you're supposed to figure out a follow set. I think that might be more relevant. But of course, for the algorithm, you should also try to understand the line. Okay, and let me see. Okay, that's fine. Okay, good. Okay, the algorithm, quickly. Okay, not many lines of code, and I will get you guys ready as well by some warm-up exercises before we get to the actual example. The input, okay, by the way, the algorithm is about get follow as opposed to get first. We are given certain grammar, okay, and what we really want to calculate is a map. Remember, we talked about the first being more like a map. You know, given certain variable or terminal you want to return, it's set of first symbols, similar for the follow set. Okay, so it's a map or mathematical function. So this part tells you it's more like a map. Given the variable, we want to figure out its set of symbols being its follow symbol. That's basically the input and output. And initially, the follow set for all the variables is simply just empty. That's easy. And there will be some very important case to start with. The start variable has the follow set containing EOF to begin with. If you remember that little case we talked about, for example here, the goal is the start variable. Itself has always got EOF at the end, always. Okay, just remember, that's what we should start with, always. And just a little reminder over here, this is the start variable. And this part over here, like a last follow, initially empty, and then we want to check to see while the last follow is not equal to the follow, and the same idea. What we really want to get into formally is get to a fixed point about the calculation of the follow. We'll put it a little bit more intuitively. For every iteration for the while loop, we want to do some updates to the mapping of the follow set or the follow map over here. If there was any updates to the follow, in that case, the last follow and the follow wouldn't be the same. That means we have made some progress. On the other hand, if after the entire iteration, we haven't really changed the follow set, that means we have reached a fixed point. The follows value is simply just stabilized. In that case, we don't really go any further. Okay, that's kind of the idea. All right, so it can be guaranteed it's always going to terminate. All right, at some point we definitely can finish the calculation. And what about this part over here? Right, I'll highlight certain parts that you should really watch out for, and then we'll see some warm-up exercises. We'll do that together. Okay, so number one. You can see we have some nested loop. But this one here is simply say we want to check for every rule in the grammar. So that part there is not that important. This is what's important. Notice that we go from k down to 1 rather than going from 1 up to k. That's the first thing to note. That means for every rule that we have over here, unlike the first set, in which case we try to calculate from here, and then maybe we have to keep accumulating if they are nullable. Now we go backwards over here. So we start with beta k with something. And then if this is nullable, we have to accumulate it and include it as a follow for the next, the previous one, and etc. So we're going in this direction. So that's why you see k down to 1. Okay? But exactly how to do this calculation here, I got some warm-up exercise for you. Bear with me. So this one here, we just go from right to left. Go from right to left for the computation for every rule. And over here, we got certain calculation here. And when you study the algorithm, I want you to pay more attention about this variable called trailer. Okay? Trailer here, and trailer here. Okay? I wouldn't really trace it faithfully. When I do the example, we can easily get lost, including myself. So, but something you may just want to convince yourself it is really doing the trick. But we'll do a little bit more intuitive tracing, hopefully. But what you want to really notice is for this particular case, okay? And for that one, I'm going to make some remark, and then we'll do exercise after that. Okay? So what I want you to pay attention to is this part here. Okay, this part here. We are checking to see whether beta I is nullable. Is beta I nullable. Okay? If it is, we do something. If it is not, we do something else. All right? If it is nullable, then we want to accumulate if beta I is nullable. Accumulates its first for the follow of beta I minus 1. Right? It's a very precise remark, but you can convince yourself that actually is the case. What we're saying is this. If beta I happen to be nullable, that means when we calculate the follow for beta I minus 1 in the next iteration, we should include the first of beta I because it's nullable. Right? Otherwise, we don't include it. Okay? Okay, for this one here, if beta I is not nullable, then don't include its first. Okay, that's some remark. You can actually look at them maybe later after we have done the example. Okay, and we're going to do two exercises together, but I'm just writing the question over here. So this will be something you will have to figure out in general. Okay, let's say this. If this is the rule that we are currently considering, okay, so we should definitely consider beta k. What will be the follow of beta k? And this is actually some special case we talk about, remember? Because beta k happen to be the rightmost components. So the follow of beta k should be the follow of A at the same time, right? That's something we did before. Number one, I can definitely put it right away. It would be the follow of A for sure, okay? Now, we want to calculate the follow of beta k minus 1. What will be its follow? We have two choices. Either we have to include the first of beta k, or we don't have to include, depending on whether or not beta k is actually nullable. All right? That's something we have to watch out for. Okay? Why don't we take a look to see what's going to happen here? Okay? Let's say we got this. I'm going to write it down precisely. So let's say A produces, let's say, only 3 components, beta 1, beta 2, and beta 3. Okay? Over here. We got 3 components here. And we got different cases. And here we're just enumerating about beta 3 and beta 2. We're talking about this one here and also this one over here, right? These two. Okay, these two. And beta 3 may or may not be nullable in general. So 2 possibilities. Beta 2 may or may not be nullable, also another 2. So we got 4 possibilities, 4 cases to consider. I'll just talk about only 2 cases. For the other 2, you can definitely fill the gap for yourself. Okay? Let's talk about these 2 cases quickly. What will be the follow of beta 3? The follow of beta 3 over here is actually quite obvious. Well, since it's the rightmost symbol, it will be just the follow of A. And this will also be the follow of A because it's simply just the rightmost symbol. That part is actually the same. Okay? And how do we calculate the follow of beta 2? Okay, let's talk about this case. Here we say that the epsilon, let me just rewrite this rule. So here we talk about A produces beta 1, beta 2, and beta 3. And we are making the assumption that beta 3 is not nullable. Okay, so we are making the assumption that this is not nullable. Okay? So what we should do is, what can really follow beta 2? Whatever that can also follow beta, oh, sorry, let me say it again. Because we know that beta 3 is not nullable, so that means whatever you can see after beta 2 will just be the first of beta 3, for sure. Okay? So this one will just be the first of beta 3. You can think about that's all we can see over here. This will be the follow of beta 2. Okay? Now, question is, should we union that with the follow of beta 3? This is a question mark. Right? We shouldn't in this case, because given that beta 3 is not nullable, there's no possibility of beta 3 to become null. In that case, what follows beta 3 is not relevant to what can follow beta 2. Right? That's kind of the logic you want to get through in your mind. So we don't include this. I wrote it there just so that you may want to consider in some cases. Okay, let's now go a little bit further. What about if we want to calculate the follow of beta 1? Okay, and we're assuming that beta 2 also is not nullable. That's also something we assume. So beta 2 over here is also not nullable. Okay, can anybody try to see what should be the follow of beta 1? Swap. I agree. Should we include the follow of beta 2? No. Because it's not nullable. Absolutely. Okay? If you are getting a little bit closer to that kind of intuition, that's a good sign. Okay? Given that it's not nullable, so the only thing we include would be just the first of beta 2. Okay? Just that. This is more like an extreme case where somehow for every symbol over here, its next symbol is simply just not nullable, so that you cannot really accumulate the trailer from the algorithm. Okay? That's something you will see when you study more closely on the algorithm. All right? How about just do one more case before we start tracing the algorithm a little bit more closely? How about this? So guys, I'll give you just maybe 1 or 2 minutes. Let's say, let me just write down the rules once more. A produces beta 1, beta 2, beta 3. And we are making the following assumption. Both beta 3 and beta 2 are nullable. There's a possibility that they might be null. Nullable. And this is also nullable. Okay? This might be the case where we have more union to actually compute. Okay? And we already got this starting point. The follow for the rightmost symbol is always the follow of the left-hand side. Okay? So you guys can think just for 1 minute, what will be the follow of beta 2 and also beta 1? Think about it. Okay? Okay, just 1 minute. Thinking ahead, we'll even write something down. That's okay. And then we'll try to work this out. Once we have done this, I think we got enough warm-up to actually trace the actual grammar. All right. We can start with maybe beta 2 over here. What will be the follow of this? You wanted to volunteer? Okay, yes, go ahead. What should that be? Yeah, I agree. Yeah, absolutely. First of all, for this symbol here, it always can be followed by the first of the next symbol. That one's for sure. So that'll be the first of beta 3. Yes, I agree. First of beta 3. He also said something else. What was that? Exactly. Yeah, absolutely. That's right. I agree. Guys, what about follow of beta 1? Maybe a little bit longer to write, but think about it. Because now we got a case where beta 2 could be nullable, and beta 3 can also be nullable, right? We want to union all the possibility together. Yes, go ahead, please. Okay, so of course we're talking about here, right? First of beta 2. Yeah, exactly over here, right? Okay, absolutely. The union, okay, so when this is actually null, then we can definitely see the first of beta 3. First of beta 3. And also when this is also null, we can also see the follow of beta 3. And of course, follow of beta 3 is simply just a follow of A, which is over here, which we can also look up in the map. All right? All right, guys, I hope at least this will give you a little bit of intuition. And let me make one more connection, and then we'll trace on the actual grammar. The way we actually work out what should be union is something called trailer when you see the algorithm. Okay? This will be the value of what you see called trailer. Should be single L, I'm not sure. Whatever, maybe double L. Okay? If you see the algorithm over here, basically you will just try to keep accumulating the trailer, either with the first or without the first, basically. And then, depending on whether it's nullable, that's basically what you do. And go backwards from k down to 1. All right, that's something you can see. All right, now the actual calculation. Okay. I think for this one here, I still put the algorithm over here, but we don't necessarily have to really trace it line by line. We can easily get lost. As long as you already got the intuition from here, it should be quite straightforward to calculate. But let's try. Okay. And I put down some guidance over here about how you should really do it. And for now, I just choose this particular order to actually do it. And if you choose a different order, it will still be okay. But it might be just be that you might need a little bit more iterations to actually get to the fixed point when it gets stable. But let's choose this one. Okay, let's choose this particular order. Before that, let's now do some initialization. Okay. So what we'll do is, let me first of all try to just execute this part over here. You can see that's the preprocessing before the loop. The follow of every variable is just going to be empty. So you can see nothing here, right? All the variables, nothing here. And then the follow of the start variable, which is go. Okay? That one there is actually just going to be EOF. That's what we start with. Important. That's a starting point, right? And then we're actually going to go variable by variable. Of course, for every variable, we'll also go production by production. Okay? Let's follow this particular order. The first one, let's say the go. All right? So we're going to look at this particular production. And one more thing to mention. Okay? Let me just go back to the algorithm. It's easier to see. I will write it down too. You can see here, whenever we are considering a rule, A produces beta 1 all the way to beta k. That means potentially we may have to update k entries in the map. We may have to update a follow for beta k. We may also have to update a follow for beta k minus 1 and all the way to beta 1. That's something we have to update. Okay, I'll write it down. It's important to notice. Okay, I'll put down here. When considering this rule, follow the map may need to be updated. Updated for k entries. Namely, beta k, beta k minus 1, beta k minus 2, all the way down to beta 1. All right, just remember that. Okay, let's now go back here. Okay, the first rule, we are considering Go produces expression. So potentially we can only update the follow entry for expression. Okay, what should we do with this guy given our warm-up exercise? We are lucky for this case because number one, there's only one component to consider. Also, that component is immediately the rightmost components, right? So that means the follow of expression would just be the follow of Go. Agree? Okay. So we just put EOF. That's all we do. Okay? And of course, that will be the only iteration we run, just one variable. And we're done with this. All right? Let's go further. Let's say we have the next one, the factor. All right? Let's now go over this one specifically. Let's say factor. Okay, let me just watch out the tongue. Okay, factor. And for factor here, let me give you a little bit of notes, hints over here. Beta 1. Oh, I don't want to actually, okay, let's say beta 1, beta 2, beta 3. And for beta 3, it's not really a variable. We don't need to update anything. And what about expression over here? What should we update it into? Well, expression over here is beta 2. In that case, it will definitely be the first of beta 3, which will be closing parenthesis. Do we also need to union with the follow of factor? That's important to note. Can somebody tell me? Henry. It's not nullable. Thank you so much. Absolutely. So guys, if you're not too sure about this, definitely make sure you review that. Henry just said exactly what you should know. All right? All right, so now for expression, what we should do is we should really extend the expression over here just by closing parentheses. That's all we do. Okay, so I'll make a little bit notes over here. This will just be the first of closing parentheses. All right? And that's it. Okay? And for this alternative over here, nothing to update, it's just a terminal. And here, no variable to update for the follow. We're good so far. Right? You can see so far we haven't really reached a fixed point just yet because we're still updating. Okay? And the next one. Let's do a little bit, maybe one or two more, and then once you feel more comfortable about it, you can just complete the rest. Let's say we do this expression. If we do expression over here, this one here, all right? One thing to note, potentially we may have to update the follow entry for expression prime and also term, potentially, okay? Expression prime, the rightmost components should be the follow of expression. We know the follow of expression already over here. Just copy that, all right? Let me use maybe green here. So the follow of this will just be the follow of expression. That means we're going to copy EOF and also closing parenthesis, which is right here. All right, that's what we start with. And then what about turn over here? All right, turn for sure is going to copy the first of expression prime. This is something we know. All right, it's going to be plus and also minus. And question, should we union it with the follow of expression? Swap, would you say yes or no? Or you want me to repeat the question? How about I repeat the question? I think that's important, okay? So now we are okay, let me repeat the question, and then also for everybody else. We are now calculating the follow for turn over here. For sure, it's going to include the first of expression prime, which we know is plus and minus over here. Now the question is, should we also include the follow of the expression? Should we or should we not? For that one, you may want to look at whether or not this can disappear. Can it disappear? It can. How do we tell? Because expression prime over here is nullable. All right? So guys, it's really important for you to see that, right? Okay. All right, so we also do that. And we also got the follow of expression, which will be exactly here. EOF and also, EOF and also parentheses. And for this one here, I would like to make a note for your review. This part over here is simply the follow of expression prime because it is nullable. Okay? I would suggest we do just one more, and then the factor can be left as exercise for you. In case you got trouble, you can definitely reach out to me. Okay? Why don't we do just one more? Okay? So far we got 1, 2, 3, 4 calculated. Okay, 1 so far. Why don't we do, so we are now done with term. Okay? Term is actually done. Why don't we try to do term prime? Okay, for term prime. And for the term prime over here, let's see where we have. Okay, it's actually here. Term prime. All right. And let's just do a little bit of rehearsal. Let's say this rule specifically. I think that'll be enough. You can complete the rest. How should we update accordingly? Okay, this one here. Right? Potentially, we should really update the entry for term prime and also factor, potentially. Right? And now, what should be term prime? Should we update it? The follow of term prime should be the follow of term prime. Well, nothing to update. Right? And term prime, by the way, is actually over here. It is nullable. Notice that. Okay? It is nullable. Okay, let's figure out the last one. Factor. What should be the follow of factor over here? Apparently, it should include always the first of term prime. The first of term prime will be multiply and divide. Multiply and divide. Should we also include the follow of term prime? Should we? We should, because term prime over here is also nullable, right? Term prime, that's something that we will calculate a little bit later. So you can rely on the further computation. Further iteration. Okay, so and etc. Okay, continue with this trend over here and complete the table. And how can you compare your answer? To find the answer, you will see that it's right over here. Okay. Okay, right here. Important exercise for you, and then I'll give you some extra as a PDF later. And we'll go over the answer on Tuesday. Start the table with empty, like what I did, and then you can feel free to go with this particular order of the variable. Make sure after you have completed the tracing, the computation for the follow, you will actually see exactly the result like that. If you can see that result, then that means you really got it. Okay, that's something I'll leave to you guys. Okay. Okay. All right, I think that's about all. Oh, well, we got one more computation to do, which is not too bad. Okay. Let me look at the time. Okay, we got about 5 minutes. Okay, how about we just go on with it quickly. Okay. That's the okay. So backtrack free grammar. Okay. So this backtrack free grammar, we're going to look at the one symbol look ahead. And given that we talk about the first and also the follow, now we are actually going to combine them together in a way. So we have a new algorithm. But luckily, the algorithm looks just like what we had before. There's only a single line I had to change, only a single line, which I'll show to you. Okay, let's go over just some bullet points and we'll show you the algorithm. So this will be the final set you guys will have to know for top-down parsing. Remember, we talk about first, we talk about follow, and this is called start. Okay, the start set is basically going to be a combination of the first and the follow. Okay, how are they combined together? Let's go over the definition here. I'll give you a little bit more hints about how you can interpret that. Okay. Okay, so this will be the ultimate definition we have to use in the algorithm. So in the actual algorithm for the backtrack-free grammar, you don't have to mention first and also follow at all. You just mention the start. That's all you mention. Okay. Whenever you're given certain grammatical rule, how can I know the start symbol conceptually? Okay. So now basically you want to say if this particular right-hand side, we want to know whether or not it is nullable. If it is nullable, okay, so this is when beta is nullable. If it is nullable, that means we should really look at the first of beta and also the follow of beta. Both. The first and the follow. Of course, the follow of beta will just be the follow of A, of course. Okay? That'll be the first case. On the other hand, if the beta is actually not nullable, is not nullable, in that case, we just don't need to worry about its follow because you cannot really go through the wall to see that. So that would just be the first of beta. All right, think about this definition. It's actually still following the same intuition as we said before. Okay? And so there is one property about a backtrack-free grammar. So later on, if we ask you about, given a grammar, is it really backtrack-free? All you got to do is to check to see whether or not this particular rule is actually satisfied. And don't be too terrified. Actually, say something very simple. If you choose any two rules in your grammar, any two productions, if their calculated start symbols do not really simply do not really overlap, in that way, you know that the grammar is backtrack-free. That means you can always have the look ahead unambiguously. Okay, that's what it means. So here, between any two productions rules, we can always unambiguously choose one. Unambiguously choose one. Always. And of course, you will be only convinced when you actually see something that's actually not backtrack free. That's something we'll show to you. Hopefully we have time. We'll see. Okay, just a few minutes. Okay, so review this definition here and also review this property, right? This property, we don't need to prove it. Just something you can take for granted, more like a definition. Okay? Okay, and then, let's look at the final algorithm. We don't need to trace it, don't worry. I just want to show you the final algorithm. Okay? And of course, for your assignment number 3, you didn't really have the computation for the start set using first and follow. If you really want to use that one, feel free. That's okay. I don't mind. But you really don't need to. Okay? But let's now take a look at the final algorithm. The only line that we have changed is this line here. Basically, only this line. Look a little bit close. Let's look a little bit more closely over here. Okay, only this line. And this line over here, remember maybe about 2 or 3 lectures ago. This line here is really to say if you got any production rule that's unvisited, we haven't really explored that, before you use it, look at what's the start look ahead symbol for that particular production. If that one matches the word you're matching, you're supposed to match. In that way, you can choose it. Otherwise, don't choose it. With this look ahead, we can basically avoid the possibility of backtrack. I'm still putting them there, but without rewriting them. But just remember, this is how you can avoid the backtrack, because you can always choose the rule that's going to work. Okay? Always choose the production rule whose start symbol matches. Right? That's how we can avoid backtrack. Okay? That's the only thing I would like to highlight. Okay? Okay, good. A very typical question is like this. Let's say you're given a grammar, context-free grammar. And then the question is this particular context-free grammar backtrack-free? Okay? I'll dive into the hints directly. Okay? This might be what you're given in the quiz or in the exam. So what you should really realize right away is what really qualifies a context-free grammar to be backtrack-free. So there was a little property which we went over last week. Okay? I wouldn't test you on that, but I can just go there directly. Make sure you study for that for next week and also the exam. Okay, so this is the input grammar over here. Okay? In order for any arbitrary grammar to be backtrack free, this is the property, which is to say that given, you can think about production number 1, number 2, number 3, number 4, number 5, number 6. We got 1, 2, 3, 4, 5, 6. 6 different productions for this grammar. We want to make sure pairwise the start set for any production rule, any 2 production rules, do not overlap. The overlap should be just empty. There should be no symbol that's common. If you think about it, it actually makes sense. This is to say, in order for us to determine the look-ahead, if the look-ahead for 2 production rules happen to be the same, in that case, we don't know which one to choose. It's kind of ambiguous, right? And we'll see example right away by doing this exercise. This is to say, no ambiguity in choosing a production rule using a look-ahead symbol. Right? That's something you will definitely see by doing this exercise. And you can see we're using the definition for start. And of course, you got to study the definition for start, which is defined using either this or this, depending on whether or not the beta over here is nullable. All right, that's by the definition. That's something we did last time. If you have any trouble understanding this definition, maybe you can recall by watching the recording. Okay, I just remind you, these are the relevant pieces of information you need. And I will give you guys just 1 minute so you can get used to this kind of question. If you look at this grammar over here, do you think you can find, let me put it this way. If you look at this grammar here, do you think it is the case for pairwise combination of the rule, for example, this rule and this rule, do they have non-overlapping start symbol? It seems like these 2, yes. But can you find any pair of the production rule that actually got common start symbol, which will break this particular property of being backtrack free? Can you find such weakness? If you can, so that means this grammar here is not backtrack free. If you cannot, then it will be backtrack free. That's kind of the story. All right? I'll give you guys just 1 minute to at least understand what the problem is. This is what you will be typically given, and these 2 are what you're supposed to know. Okay? Just to be sure. Okay. Another 20 seconds. Okay. All right. Number 1, do you think this grammar is backtrack free? Yes or no, first of all? Anybody? Any thoughts? Henry, please. Yeah. Yes, I agree. That's good. Okay, thank you. Let me just elaborate a little bit more, okay, about what you're supposed to write in the quiz or the exam. So guys, it's okay not to be able to respond at the moment. I understand that, but you got to study for that, okay? It's, if you are behind the lecture, please catch up. Okay, so here the answer is no. Because we will be able to find two production rules where their start set are actually intersecting with certain start symbol. Let's say, for example, this one here, and also this one here. Let's say these two production rules. All right, so I'll just give you one example here. Let's say for this one here, what is the start set of this rule? We got factor produces the name. What would that be, right? This one is actually easy. If you look at that, in order to calculate the start of certain production rule, you want to consider what is the first set for beta. In this case, this is beta. What is the first of name? Well, just the name. It's only a terminal, right? That's something you want to see first. Okay, so here, if you think about the first of the name over here, would just be just the set of symbol, just one, just name, right? So that's the first set, because the epsilon is actually not there. Because it is not there, by definition, the start set would just be the first set. So it will be just the name. And if you apply the similar reasoning, the start of this particular production rule is also the name. Right? So now you can see that for these two production rules, you got overlapping first symbol. So that means it's not backtrack free. Intuitively, what does it really mean? Let's say if the current word happen to be name. In that case, you wouldn't actually know whether to choose this one here, or this one here, or this one here, like what Henry said. You wouldn't know how to go. Either this one, or this one. If you're lucky, you might choose the right one. If you're unlucky, you may need to backtrack, which is not good. Right? So that's why this grammar over here is not backtrack free. And for this particular non-backtrack free grammar, we have the so-called common prefix. So we can fix that quite easily. So this guy over here is so-called common prefix. And we can fix it so that it becomes backtrack free. Okay, so if you go back to the slides, you will see exactly what I just showed to you. You can just go over them. Okay, and it's also very important for you to look at this conclusion over here about why intuitively it's not backtrack free. Because when you got a name to decide, you wouldn't know which rule to go to. You got three candidates. Robbie. Nope. So here, if you look at the rule, for example, let me just go back to, okay. If Robbie might be talking about here, right? Yeah. Okay, that one is actually not relevant here. Because if you talk about the first set of this particular rule, this one here is already a terminal. So you don't have to continue to look at the next one. It's already blocking. That's the only one you see, which is the name. Okay, good question. All right. So guys, what Robbie just was asking was, should you consider this one? No, because before that, it's already a terminal. All right, according to the definition for calculating the first. All right. And what we want to do for this particular kind of violation, we can have something called left factoring, which is quite straightforward. Let's see how we can do it. Let's go over some slides, and then I'll show you how you can fix it. Okay, left factoring by factoring out the common prefix into just another non-terminal, like a variable. That's what we can do. And so these are the steps over here. Let me go over them with you very quickly, and then we'll see how we can apply that into the grammar. Okay, let's say this. This part here, of the grammar is problematic. This part over here. Because we have the common prefix alpha. Alpha, all the way to alpha. Whereas for gamma over here, they don't have any occurrence of alpha. So they are not part of the problem. Only the purple part, which I just highlight. And that's actually the general case, because not necessarily every alternative in your production of your variable production should be fixed, not necessarily. Okay? So how can we fix them? We just want to fix this part over here, just this part. So what we can do is we can simply say, you can say here, this is a common prefix, alpha, we'll simply put it here. And then after that, it can be either beta 1, beta 2, or beta n. So they are basically turned into just another variable, beta 1, beta 2, all the way to beta n. And for the rest, gamma, we simply just put them here, just the same. That's the general rule. But let's apply that right away. So here you can think about this part over here is the alpha. This part. This part over here is the alpha. And then this part over here is this nothing here, like epsilon. This is like a gamma 1. So this is, beta 1. Beg your pardon. So this is like a beta 1, like a beta 2. And this part over here is beta 3. Right? And actually, luckily, we don't have any gamma in this case. Right? We don't. Every production rule, every alternative over here simply start with the common prefix. That's why we don't have any gamma. Okay? Now, how do we turn that into something that's actually not, that doesn't have the common prefix? All right? So we can simply say, for example, factor over here, according to the rule, we're going to have, first of all, start with the common prefix first, name. And we create some new variable, maybe arguments. That's what you will see on the slides. Okay, and then arguments over here, according to the rule, is going to be gamma 1 or gamma 2, just going to be all the beta over here. Arguments will be either this or epsilon or this. Can be epsilon, can be argument list, or it could be argument list. Right? That's what you will see on the slides. Let's try to revisit this right away. Is the grammar that has been fixed now backtrack free? Right? We're thinking this way. What used to be the problem, is it still a problem? No, it is not. Because if you look at that, this part over here, the first symbol, and this part over here, the first symbol, they are now different. Of course, if you try to consider this rule, they're also different. So you can easily distinguish. So that's why it's not, it's definitely backtrack free. Right? Okay, so you want to, this over here will satisfy the backtrack freedom property. All right. All right, so that's about left factoring. Okay, are you guys okay? Right? Let's recap what we have seen. What you might be given is simply just an arbitrary grammar, in which case you might be asked, is it backtrack free? In order for you to determine that, you have to consider this property, meaning that pairwise production rule should have non-overlapping first symbol. If there's any overlaps, that means it's not backtrack free. Right? So of course, you got to know how to calculate the start. In order to know how to calculate the start, you have to know how to calculate. You need to know how to calculate first and also follow. Right? That's something you will have to review. Okay. And we have spoken about it, which is good. Okay, so let's now review quickly about what we have seen. We're getting to the very close to the end of top-down parsing. So given an arbitrary grammar into a top-down parser, right? So far we talked about two issues. One is about termination. The other one is about backtracking. Question for you guys. How do we avoid non-termination for top-down parser. What does the input need to satisfy? What kind of property do we need? If you guys remember. Colleen, do you seem to remember? Absolutely. Thank you so much. If it's left recursive, you got to remove it, convert that into right recursive. Thank you. And the next question would be, how can we minimize backtracking or to remove the backtracking? That's basically what we have talked about in the last few lectures. There are two things. Let me just get to review them right away. You may have to do some left factoring for sure, and also the main thing is about having that one symbol look ahead. So that means you want to calculate the start set, right? So these are the two things. All right, so let's talk about some properties here. So this is some property which we don't have to prove. Not every context-free language has a corresponding backtrack-free context-free grammar. So is it just a property here? So let's consider this here. So let's say you have certain language, let's say you have some context-free language I. If you look at the formulation here, I is here. And if I simply ask you the question, is there any backtrack-free grammar such that its accepting language is exactly I? This problem over here is undecidable. It's not possible for you to write an algorithm to find that. Okay? That one's for your knowledge. On the other hand, if I ask you another question, I give you a grammar, and I ask you whether or not it's context-free. That problem there will be decidable, which we just did. What should we do? You got to check to see whether this property over here will satisfy. Okay? So this slide here, you want to make sure you understand these two, this problem over here. Given a language, you want to know whether or not there is a context-free grammar that's backtrack-free. That problem there is undecidable. On the other hand, if I give you a grammar to decide whether or not it's backtrack-free, that one there will be decidable. Right? So these are two different problems. Okay? All right. And then I think one more. Okay, and then maybe one or two more slides, and then we can give you the exercise, and then we can take a break. Let's now go over some final definition. So there is this so-called recursive descendants parser. Okay, that's some term you might actually run into when people talk about compiler. Okay, whenever we talk about recursive descendant parser, we are basically talking about top-down parser, about top-down parsing, and we're going to talk about bottom-up parsing as well, but it's not recursive descents. And it will be structured as a set of mutually recursive procedures. So this part here, I'm going to give you some flavor about how it can be implemented. But this is usually done by some parser generator like an Antler-4. You never have to actually do this by yourself. But you just need to know about roughly how it should be done. Okay, and then we'll look at the example in just a moment. And then, let's see here. Yeah. So given some grammar, the tool such as a parser generator like an Antler-4, internally they will actually calculate the first, follow, and start set automatically for you. But you ought to know how to calculate them if you had to do it manually. And efficient, okay, LL1. This is something you might see later when people talk about compiler, LL1. LL1 here, every bit of the name has its meaning. Meaning that L here has a meaning, L here has a meaning, 1 here also has a meaning. Okay, let's talk about it. Since we talk about top-down parser. The first L means the input is going to be processed, the word in the algorithm from left to right. That's the first L. Do you want to take a guess what the second L is for top-down parsing? What are we really trying to find out using top-down parsing? What kind of derivation are we trying to find out? Do you guys remember? What derivation? Robbie? Leftmost derivation, thank you. Left. So the second L means finding leftmost derivation. When we talk about bottom-up parsing later, it's going to be about rightmost parsing. So we're going to see another kind of parser. We'll change the second L from L to R. Okay, just remember the naming. And the 1 here means we are simply having one symbol look ahead, the start symbol, right? So LL1 parser over here actually kind of summarizes what we have talked about so far about different ingredients for the parser. Okay, top-down parsing, processing the input from left to right, finding automatically the leftmost derivation with one look-ahead symbol to avoid backtrack, basically. Okay, good. Okay, and let's see what else. Okay, let me see. Oh, I think just one final slide to show. Okay, this one here, I'll show you briefly. So this fragment of code just gives you a taste about how you're supposed to implement the LL1 parser, okay, given the rule. Okay, I'll just show you quickly how you can read it, okay, quickly. Let's say we have a part of the grammar over here, expression prime, which can either go for this way, or this way. And remember, we said the parser is supposed to calculate automatically the first set, okay, the start set. And sometimes you might see first plus, but this really means the start set. That's the name we'll actually use, start. Okay, the start set, which can be either plus or minus, meaning that if the word that we want to match happen to be plus, you definitely choose this rule. If it happens to be minus, you choose this one unambiguously. And if it happens to be nothing, EOF, or closing parenthesis, you choose this one here, right? That's kind of what the rule really means. And this one here, let's see what it is trying to say. First of all, you can see this non-terminal expression prime. It will be implemented as a function called expression prime. Okay, it corresponds to that. You can think about every non-terminal, every variable in your grammar is going to be turned into a function. And the way you structure the function is going to be a list of alternatives. You can think about alternative number 1 might be just here. And another alternative might just go here. And if none of them actually matches, you're going to return false because none of them match. Okay, let's dive a little bit more into detail. So here we're being just a little bit more efficient. Let's take a look. So here, if you read it over here, we'd say if the current word matches either plus or minus, that means either match plus or minus over here, in that case, we're going to actually try to match turn the next. That's why you see the turn. Whatever that's returned back from the turn, we're actually going to, well, this is to say, if the matching the turn actually succeeded, we're going to try to match expression prime, the next. Otherwise, it would be a failure. All right? We could basically just follow the rule. You can see the way to implement this rule is actually very tedious. So that's why the parser generator like n to the 4 can generate stuff like this for you. But you ought to know the theory behind. Right? If you go a little bit further, you can see for the other alternative, if the word is simply closing parenthesis or EOF, in that case, you will go for rule number 4, which is over here. In that case, nothing to match. You just return true. You succeeded. Okay? Otherwise, if none of the alternative actually match, you will just return false. It's a syntax error. So this fragment of code actually kind of summarizes about how you're supposed to implement a recursive descent parser based on the first set. Okay, that's something we have spoken about earlier.